So we've talked about integration, first of all, symbolically as an antiderivative. Second of all, numerically as this Euler approximation. And then we just did it third, graphically using slope fields. So now I want to try to sort of bring it home and wrap it all together. Okay. So what we did with Euler approximations was the following thing. We said, now if it was just a linear approximation, you would stop here. F of x is approximated by f of a plus f prime of a times delta x. So delta x being, if you think of it as from the tangent line, that would be x minus a. Does that make sense? And then this is the short form of, just as a reminder, it's like y minus y1 equals m x minus x1. So I've translated everything. I've called this delta x. M, of course, is the slope, so that's f prime of a. And y1, I've pushed it to the other side, and that's just f of a. Oops, f of a. And y is f of x. So I'm going to write, I'm translating between using y notation for functions and f of x notation for functions. From now on, I'm going to hope that you're kind of familiar with that translation, and I'm going to stop talking about it explicitly. But you can always do this translation if it helps you. Okay. So with a linear approximation, we would just stop here with one term. But what we saw with Euler approximations is that you can get a better approximation if you just add in more stopping points, which means adding in more terms in this expression. And that looked like this. Oops. Okay. Yeah.
From what I remember, didn't we decide that every time we jump by delta x, which means it should be the first one should be f prime of a times delta x plus f prime of a 1 plus delta x?
Ah, okay. So you're exactly right, but that's what's explained in the next sentence.
Okay.
So this says, so where each ai is an x value, and they are evenly spaced by delta x. So for example, if your a is, let's say your starting value is 1 and delta x is a half, then your a1 is going to be 1.5, and your a2 would be 2. Your a3 would be 2.5, et cetera, et cetera, et cetera. So that's what that explanation means. So you're exactly right. Okay. So I just want to make sure everybody understands that we did it before with numbers, and now I'm just translating the numbers into a general formula using constants and variables and stuff. The calculation we did last time as a formula is just this. Okay. So right now we're going to go through the process of formalizing this and making this, I want to go on the journey to make this a nice notation and have it no longer be an approximation. Okay. So first of all, changing the notation. So we can rewrite this using summation notation. Okay. So let me ask this. Who in here is familiar with summation notation? Okay. And who is not? Okay. So what is summation notation? Summation notation is a way of saying I'm adding up a bunch of things, and they're all kind of similar. And in fact, I can all describe them in the same way. So instead of writing out every single term, I'm going to write out what that term kind of looks like, and I'm going to say I'm adding up all those just with this one expression. So what do I mean by that? Well, what does every single term look like? It's f prime evaluated at some value times delta x. So the only thing that changes in every single term is what is that x value? So that's what this summation notation wants to say. And let me be a little more precise about this notation. So this says I'm going to take here we go. So here's the thing that I'm going to add up. So I'm going to add up f prime at some value times delta x. So the thing I need to say is this. Actually, I equals 0 to n. Okay. So what this tells me is that I'm going to add up these terms starting at I equals 0. You can read that. And counting off. So I equals 0, I equals 1, I equals 2, I equals 3, blah, 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 all the way up to I equals n. And you can just, so all it is a fancy a compact notation for instead of writing this whole thing out. And that's all that summation notation means. Instead of writing it all out, I'm saying I'm gonna add up all these terms, and each one is described in this way. Okay. So for example, if I wanted to, just a quick little side example, suppose I wanted to add up 1 plus 4 plus 9 plus 16 plus 25 plus blah, blah, blah. How could I write this? What does every term have in common? What's special about all these things that I'm adding up? They're all squares, right? Yeah. So in fact, it's really 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, blah, blah, blah. Huh? Okay. So how could I represent that using summation notation? Right. Right. Starting at I equals 1 up to, I'm just going to say up to n, so I stop wherever I say I stop. So that's what summation notation does. It says I'm adding up all these terms. Each term can be identified in this way.
It's not I plus I square because it's 1, 4, 5.
So I starts at 1, so 1 squared is 1. Then I goes to 2, 2 squared is 4. I goes to 3.
Oh, I'm sorry, I thought it was a 5. That's what I mistake.
Yeah.
That's what I said. Okay, now.
Right. Always adjust for the fact that my handwriting is not awesome.
No, it's awesome, Professor.
Okay. Okay. So this is what summation notation does, and this is how we're using it in this particular example. So every term looks like f prime of some value times delta x. So I've just put in a little I here, which is called an index, to show that every single time, first I've got a0 is some value, and then a1 is some value, a2 is some value. And what values are they? Well, I use this sentence to describe what they are. Okay. So, okay, great. So what we saw last time is that if you just leave it like this, this is an approximation, right? So this says I goes from 0 to n. I guess technically that should be n minus 1, but whatever. So this is the formula for an Euler approximation with n steps. So if we wanted this approximation to be better or better, what should we do? More steps, right? And if you think about why that makes sense, just go back to the graphical representation. If instead of going a long distance, well, actually, let's go back to the discussion that we had last time, which was The original Euler approximation, even though we didn't know it when we learned it, is just using the tangent line. Using the tangent line is an Euler approximation with one step, because you're only using one tangent line. And the first thing we did last time, we just said, oh, well, let's break this down, and let's use, what did I use, 4 steps?
3.
This one was 4 steps. Okay. So if I use 4 steps, then I'm going to get something, then my little straight line approximation is going to be closer to the actual graph that I want it to be. Okay? Well, just keep pushing that further and further. The more steps you use to get to your destination, the more exact your approximation is going to be, the better it will be. So if we want it to be as good as possible, how many steps should we use? Infinity, exactly. Okay. Now saying we want an infinite number of steps is the same as saying what about delta x? We want delta x to be as small as possible. Smaller and smaller and smaller, basically going as close to 0 as possible.
Like a limit to 0.
And that's exactly what it is. And this is something that you've actually already done. You already did this for derivatives. You take the limit as delta x goes to 0. Now when you learn derivatives, the notation for that, you often used h, and you said the limit is h goes to 0. H just represents delta x. So it's the same thing. Okay. So what we want to do is we want to do this. Take this little summation expression, the sum of f prime of a sub I times delta x, and want to take it as delta x goes to 0. Now I'm skipping over some of the notation because it's not important. I just want to get the ideas down. So when you take the limit, instead of writing limit every single time, instead of writing limit as delta x goes to 0 summation blah 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 blah, we have a notation for that, and the notation for that is this. So in this fancy new notation, delta x is now written as dx, and the sigma for sum becomes this sort of long squiggle, which is called integral. So that's actually the origin of these symbols. So sigma is actually a Greek capital S, and it stands for sum. The integral symbol actually started out as an S for sum, and just over time it got stretched out. So it was always intended to be understood as a sum. Then it was invented in the, I don't know, some centuries ago. So this is now our notation for the exact answer. Because we've taken a limit, as we've seen before, the limit gives us something that is exact, not an approximation. Okay. Now, as much as I hate to do it, I have to add in one technical detail here. So, writing it this way, there's a problem with the letter x. We're using x in 2 different ways, which we really shouldn't be doing. So on one hand, we're saying f of x, starting out over here, is the x is like the final point where I'm going to as I approximate my function values. But then we're also saying x is the variable of some function called f prime. So they're 2 different things. So we can't really do that. So technically speaking, we solve that problem by saying we write f prime as a function of t. Right? Because in terms of notation, you could write f of x, you could write f of t, you could write f of alpha, it doesn't matter. So we don't want to we want to make those two things separate. Anyway, it's a small technical point. I don't want to spend too much time on it. But it does explain why when you see the formula written, the formula is written like this.
Shouldn't it be the integral from a to t?
No, because that's the other rule. Okay. So I didn't explain. Sorry, I didn't explain those things yet. Where's my explanation for that? Okay. It's right here. Okay. So give me 1 second and I'll explain what that a and x is doing there. Okay. So what we have is by taking a limit and making this statement precise, by turning the approximation into an exact value, this is called the fundamental theorem of calculus, number 1. Which says that, well, it says that. Okay. Now, so in this case, I've said we're going out to some future value. I don't know what it is. Let's call it x. So this is really making a function. It says if you tell me what that future value is, then I can. Before it was approximated, and now it's say exactly what this is. Okay. Now, what if I give you an actual future value, the way we did with Euler approximations? If I actually give you a future value, let's call that, I don't know, b. So you just plug that in, and now the statement looks like this. So, and notice that sometimes I put the f of a on the other side, like y equals y1 plus, and sometimes I put it on this side. So this would be like, in this final form, this is like y minus y1 or y2 minus y1. So just keep in mind that depending upon, I don't know, which textbook or which formula, it could be on either side. Obviously, both are correct. It's just a question of the form of how you write it down. But that's the idea of what's happening. Okay. So when we write it like this, when we're talking about going from a specific x value a up to a specific x value b, then this is called the total change theorem. Talking about a specific change. If you simply say, well, I'm going to go out to some future value, I don't know what it is, so let's call it x, this is really a function. And this is quite fancy, and that is the fundamental theorem of calculus. And we're talking more about these things. Question? Yeah?
There's no significant difference between those? Just a specific point?
Exactly. Right. Okay. So let me make one comment. Okay. So two things. Actually, I'll make two comments. So first comment. Notice that the x value where you start and the x value where you stop in this notation is written next to the integral symbol. So we would read this as the integral from a to b of blah, blah, blah. So now those things have names. So I call them the starting point and the ending point. The technical terms for these are the limits of integration. Oh my God, that's a terrible name because it makes you think of limit. And it has absolutely nothing to do with limit or taking a limit. So I will sometimes just call them the stopping point and the starting point just so there's no confusion. But you should not confuse the two. They're also called the boundaries of integration. Absolutely. There you go. Okay. That was the first thing I wanted to say. Second thing I wanted to say is I just noted this technical point where you can't really have x serving in two different roles, so we use t over here. If you're lazy and ignore the xt variable conflict, it's not a major issue. You can kind of get through it. So if that confused you and bothered you, it's not going to turn out to be a big deal, and I won't be too particular about it. Okay, that's what I want to say about that. Questions?
No, I think I'm starting to understand because it's
Okay.
a and b point, and that's f of a and f of b.
Exactly.
Okay.
Yeah.
Then
Right. So what we have on the right side of these equations, you should just think of this as notation. This is notation for stuff that we already kind of know about. So this is integral. Your starting point is a, your stopping point is b. F prime of t is the function that you're given, and dt is, well, it's called the differential. We'll talk about that later maybe. But if you want to remember what this means is f prime is some function that you're given and you're trying to figure out what f is, first of all. And second of all, technically what you're kind of doing is taking a sum on this function using, well, in this case, dt, so using a delta t. Only we've taken the limit as delta t goes to 0. So what we know is that instead of having to do Euler approximation with like 100 steps, 200 steps, blah, 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 what we know that we're allowed to do is, well, if I'm given f prime, all I really want is my original function f. And we've already talked about how to do that. For example, if f prime is 2x, what's the original f? X squared. So this is plus c. So this is a problem that we know how to solve. For example, here we go. F prime of x equals x cubed plus 3. F of 2 equals 4. Let's find the original function f, and then let's also find f of x, and let's also find f of 5. Okay. So what do we do?
First you take the antiderivative of x squared x cubed plus 3x, x to the 4 over 4 plus 3x plus c.
Okay. Right. So one way to do this is to say f of x equals x to the 4th over 4 plus 3x plus c. Okay.
And you set x to 2 and equal. I mean, you set x equals to 2.
Mm-hmm.
So 4 equals to 2 to the.
What was it? 2.
You solve for c.
And you can solve for c. You get 4 equals, so 2 to the 4th is 16, over 4 is 4, 3 times 2 is 6, plus c. So what is c? Negative 6. Okay. So now we know that f of x equals x to the 4th over 4 plus 3x minus 6. And now we can also say what f of 5 is just by plugging in. Uh,
620.
yeah, 625 over 4. Okay. So 160. Okay. So if I did it correctly in my head, that's the answer. Okay. So does that make sense? Y'all? Okay. Is there anyone that's confused by what I just wrote?
Why did you put
Yeah.
0.25?
What I put? Sorry?
Why did you put 0.25?
Because that's what it is. 5 to the 4th divided by 4 is that.
Oh.
It is okay if you don't give like s to 2 is equal 4. How can we find it?
If, I'm sorry?
If in a case that you don't give like s2 equal 4, how can we find c without?
You can't. That's the point.
Oh,
Yeah. If you're not given this, then you have to stop here. Yeah, that's the whole, and that's kind of the point.
Why did you put the 4 in the front?
Which 4?
The second one.
Because f of 3 equals to 4, so you set the whole equation equal to 4.
Oh.
I mean, yeah, it might have been nicer if I just wrote it like this. F of 2 equals that, so 4 equals blah, blah, blah. Maybe that's a nicer way to write it. Okay. So,
Yeah, but now
yeah.
if we're gonna see the second step, we're gonna see why you find the 4.
Oh,
Not gonna make that.
It's the same thing, but maybe this is a nicer way to write it down.
How would we do it
You just use the
using the Euler?
Oh. So to do, okay.
All
So,
the steps.
so a question about Euler. So, can you find f of x using an Euler approximation? You cannot. Because I'd have to tell you 3 steps, but 3 steps until what value? You have no idea. So there's no way to do an approximation of just f of x. You would need to do an approximation to a particular x value. And at that point, and you'd have to say, okay, so my starting x is 2, my ending x is 5. How many steps do you want? You can just make up a number of steps.
Euler always has to be a bound integral.
Absolutely. Okay. Okay. So that's one thing. So I'm going to need this room. So let's do this.
Wait, but in this situation we do have a bound because we have x is 2 and x is 5.
Yeah, no, exactly. I said if you're being asked what is f of 5, then you have an ending point. If you're just being asked, tell me f of x, there's no ending point. You don't know how far your steps are. You don't know where you're going. Okay. So this is one way to write this down. So almost everybody prefers the way that I just wrote, which I'm going to call the plus C approach. So there is another way to write this down, which winds up with the same answer, and it more directly uses the form of the fundamental theorem. So some people find it confusing, but I'm going to write it down because it'll come in handy for a couple of problems. You can do problems either way, either using the plus C approach or what I'm about to show you, which I'm going to call more like the fundamental theorem of calculus approach. Either way is okay. But let me show you this other way. So let's literally write down the fundamental theorem of calculus using this function. So what we know is f of x minus f of 2 equals the integral from 2 to x of f prime, and I'm going to switch to t just to be precise. And f prime is t cubed plus 3 dt. Okay. So all I've done so far is I've just written down the fundamental theorem of calculus using the numbers that I've been given, using the formulas numbers that I've been given. I haven't solved anything yet.
You can use the plus C that one.
I'll explain where the plus C is. The plus C is hidden in here, and I'll explain where it is once I finish. Okay. Now what? Well, we know what f of 2 is. We know that that's 4. Okay. So we also know t cubed, so the integral from 2 to x of t cubed plus 3, we know what this is. This is the antiderivative, which is t to the 4th over 4 plus 3t. And then what we want to do is we want to plug in right. You sort of want to plug in for x and then plug in for 2 and then subtract. So the notation for that is like this. So you get x to the 4th over 4 plus 3x. So here I've plugged in x. Now I'm going to minus plugging in 2. So when you plug in 2, you get 2 to the 4th over 4 plus 3 times 2. Okay. All these fractions, I need a little more room. Okay. So this equals x to the 4th over 4 plus 3x and this is x minus 4 equals blah, 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 minus, when we calculate that, you get 16 over 4, which is 4, plus that, so you get minus 10. And now all that's left to do is to get f of x by itself. So we add 4. So clearly you can see this works. Now it's confusing because, as you said to begin, where's the plus c? The trick is the plus c, this constant, is already built into the fundamental theorem of calculus. Where is it? F of 2. It's right there. So f of 2 is the constant in the sense that it's the value you're starting at. And you also get it, well, technically you also get a contribution to the constant from this part right here. So long story short, this thing combined with this thing, when you combine everything and sort it all out, that's going to wind up giving you whatever your plus c should be. But the idea is that the constant is already built into the original formula.
I like this better.
Okay. So this one is sort of like mathematically more compact because everything is already written in the original expression. But a lot of people like the plus c method because it just looks like algebra, which it actually is. So clearly they're both correct. Whichever one you want is fine. Okay.
It's like the completing the square method. It's like blows your mind.
Okay. Okay. So let's together work through some examples. Okay. So first of all, find. So now we're going to use this. So now when we want to find, so now I can ask this question about integration in two different ways. I can say, here's f prime of x. What's f of x? Which is what we went through last time. Or I can ask it like this: find the integral of cosine x dx. So what's the answer to this question?
Sine x plus c.
Sine of x plus c. So these are two different ways of asking the same thing. You dig? Okay. Now, what if I ask this question? So first of all, you tell me, how do you read this? Right. So the integral from 0 to pi of sine x dx. Okay, so how do you do that?
Sine from 0 to pi.
It's gonna
Plus find the antiderivative.
Right. So what's the first thing you have to do?
Antiderivative.
You have to find the first. You have to find the antiderivative,
Yeah. And then
which is what?
Negative cosine.
Remember, it's negative cosine because it's the antiderivative. You're going backwards. Okay. So now we've got negative cosine x.
from 0 to plus c.
Right. Okay, so plus c, and now we have to evaluate it at 0, evaluate it at pi, and then subtract. Okay. So, and the notation for evaluate 0, evaluate pi, and then subtract, once again, this is the notation for that. Okay. So let's do it. So you plug in, so you got negative cosine pi plus c minus negative cosine 0 plus c. Okay? And so what do you get? So cos pi is negative 1. So it's negative negative 1, which is 1. And then you get cosine of 0 is 1, so minus negative 0. Sorry, minus negative 1, which again is plus 1. Now what happens to the plus c? Plus c cancels out. And in fact, whenever you do an integral where you're given these boundaries of integration, the plus c always cancels. So in fact, nobody ever writes plus c here, because it always cancels. And then the third one, I've given another example. So find the integral from 0 to t of cosine x dx. So first thing you need to do is cos x, you need to find the antiderivative, just sine x, and then you evaluate it from 0 to t. Oh yeah.
Negative cosine pi, is it a negative one?
Well, cosine pi is negative 1. So it's negative negative 1. Okay. Okay. So sine x evaluated from 0 to t. So that gives you sine of t minus sine of 0. Sine of 0 is just 0, so you get sine t. Now a quick comment on this. Notice that the answer to this question is not a number. It's a function. Why is it a function?
Because you evaluated t, not like a number.
Because look at the boundaries. The boundaries are 0, okay, but t. So in other words, I'm not really telling you what it is that we're trying to find. I'm saying for some unknown boundary, what would the antiderivative be, if you like? So in other words, if you tell me the boundary, then I'll tell you the answer. That's a function. Does that make sense? Okay. And just from a very simple point of view, if you start with a variable, you're going to finish with a variable. Okay. Yeah.
That one, evaluating from 0 to t, there's a different notation? Like, that just...
No, that was just me being sloppy. So, I'm sorry, I wasn't being sloppy. Let me be precise. There are different notations for it. So, one notation is to use these brackets, and another notation is just to use this bar. So I think using the bar is the lazy notation. Either one is correct and either one is understood. Yes.
Is it always negative? Is it always minus sign or is it plus sign?
Where?
After you did sine of x over to the t, then you put sine of t minus sign. Isn't it plus or it's always minus?
In between?
Yeah, it's always minus.
It's always minus. Where does this minus come from?
From the
difference.
the line equation, the x minus
Yeah.
x1.
It's just this, f of b minus f of a. So that's what that means. Yeah, it's just y2 minus y1.
And for the first one you put negative cosine pi plus c, and then you put a minus. And then you put in brackets minus cosine. Why is that all in brackets and why is the second part like not in brackets?
Oh, okay. So you're right in that I should have been careful and consistent and just put that in brackets. So I'm putting it in parentheses in order to emphasize the fact that it's one whole thing minus another whole thing. So in this case, what's the first whole thing? The first whole thing is this expression plug in pi. And the second whole thing is this expression plug in 0. And you subtract.
And you look for the sign, because it's negative. So
Right. And so, in fact, exactly as you just said, you should always put the parentheses there because it's always going to be minus, and there's a lot of times there's going to be a bunch of terms in here. You have to distribute to negative.
So it shouldn't be 1 minus 1 since it's
But what's cosine 0?
Yeah.
Okay.
So shouldn't we put the second part in brackets, so we don't need the brackets for the second part?
It is in parentheses.
The second part for sine of
Oh, yes. I mean, yes, technically I could put sine t and sine 0 in parentheses, but I was being lazy because I know sine t is just one term, so it doesn't need parentheses. But yes, you would never be wrong. You would always be right if you put each one in parentheses. It's just here I know I don't need it.
Will this be on the homework? I mean, if we have one, we have it.
Let's see. Let me talk about that at the end of class, which I know is soon. Okay. Okay. So here is another problem similar to the one we did previously. So if g prime is cosine x and g of 0 is 1, let's find g. So how do we do that? Actually, you do it yourself. That's the question. Yes. Okay. So how does this problem go? Oops. Okay. Okay. Okay, so the answer is sine x plus 1? Okay.
Wait, isn't it plus c?
Okay. Right. So g prime is cos x. So that means g is cos x, is sine x plus c. But then what do we do?
You plug in the 1.
You plug in the initial condition.
So it's 1.
Right. And so here it is, again, written out two different ways. You can either doing it, so in the first column I wrote it out using the FTC, and in the second column it's just done the plus and that. By the way, I'll be referring to the fundamental theorem of calculus as FTC, pretty much always. Okay. Is that okay? Question? Yeah.
What's that? That's the integral of 2 and 4?
I'm sorry?
That's the integral of 2 and 4 cosine? I can't see the number.
Oh, the cosine. This is the integral from 0 to x. It's a little blurry, sorry. Yeah. Okay. And so let me make the comment. I wanted to return to what I said before. Remember I said there was a conflict between using the x in two different roles, and technically it wasn't correct. So on purpose, I did that here. So here I just used x for everything. So I said the integral from 0 to x of cosine x dx. Now technically you're not supposed to do that, but notice that you can kind of get away. You can get away with it in the sense that you say you get sine x, plug in 0, and plug in x. So here you're doing this weird thing where you're saying plug in x for x, which is a weird thing to say. So, but that's the conflict. As long as you can know, as long as you're not bothered by that, then the conflict is limited and resolved.
What's the easiest way to do this?
The easiest?
Yeah.
Whichever one you like.
I don't know which one I like though.
Okay. Well, then I guess you have to pick. Okay. I'll say this. The plus C method in general is easier because it's algebra. The FTC method is more universal for some examples that we'll be seeing over the next week.
We'll have to memorize that.
What are we going to do with the
You will definitely have to know the FTC anyway for some other examples that we're about to see coming up. So wait, I got like 1 minute, so let me try to do these things.
Wait.
Okay, question? Question.
I was asking
I have to resolve that, so I'll get back to you on that. Okay.
So the due date is we have no.
Okay. Okay. So, in the interest of time, let me get to this. Let me get to this final point here, which is the following thing. Now, I mentioned this before, which is that sometimes we talk about dealing with f prime and f is one notation for talking about derivatives and antiderivatives. The other notation that is often used is to talk about starting with your function f. Then what's the antiderivative of that? And we call that big F with a capital F. Okay, so let's now use that f relationship notation in order to say what the fundamental theorem of calculus is. So we can just rewrite the fundamental theorem of calculus using little f and big F. And it looks like this. So you'd say the integral from a to x of little f of t dt equals the antiderivative, so big F of x minus big F of a. The only thing that's different is how I'm writing f. It's the same thing. Does that make sense? Okay. So if it was up to me, I would just use the f prime notation because that's the proper relationship. However, pretty much all textbooks write the fundamental theorem this way, which is correct in its own way. So I have to show you both. But the important thing is the relationship, understanding which is the function and which is the antiderivative. And once you know that, then you understand it. Okay. Let's see. And here are some examples that I'll fill in because we don't have time. But I think we've done a bunch of examples and you get the idea. Okay. Okay. So what we've actually completed now is we understand antiderivatives. So not just symbolically, but we understand the idea of if you give me a function, what's the antiderivative? It's something plus c. But we also understand how to evaluate it if we are given actual bounds for that integral. Okay. So let me just make one terminology comment. This one right here, where we just say the integral of cosine x to sine x, that's called an indefinite integral. Now, however, if I give you boundaries of integration, like in the second one, that's called a definite integral. Now you see the only difference is with a definite integral, you have to do some plugging in. Okay, so that was just a bit of terminology. Okay. Yes.